Okay, I decided to make another video on the logic of hypothesis testing, just so we can get a feel of what this is and how we're thinking about things. So I'm going to do this in a context of a multiple choice test. So Jake takes a 50 question multiple choice test. Each question has four choices. He claims to be a random guesser for tests like these, but his recent grades make his friends suspect that he actually knows the material and is not guessing. In other words, he scores better than a random guesser would. To test their hypothesis, his friends give him a 50 question multiple choice test over similar material. Okay, so what are the hypotheses that his friends are testing? So, first of all, um, what do they expect to be true? So, the expectation, what you expect to be true, is called your null hypothesis, which I've used that word a few times now. This is what you expect to be true. Well, according to Jake, Jake claims he is a random guesser. So what they expect to be true is Jake is a random guesser. Okay, so that is their first hypothesis. That's their expectation. What is the alternative hypothesis? In other words, like what's their alternative explanation if Jake is not a random guesser? Well, according to what they think if Jake is not a random guesser, then Jake is better than a random guesser. They could have said Jake is worse, but they think he scores better right here than a random guesser normally would. So that's his null hypothesis, and that is his alternative. Their null hypotheses and alternative hypotheses. So let's keep going here for a second. So we're going to try to test these and figure out what's going on here. Um, so Jake expects himself to be a random guesser, which actually means that he has a 25% chance of getting any question correct. Okay, so that's the expectation. I wrote this now. What does that actually mean? If he's just randomly guessing for every question, there's four choices for each question. That means he has a 1 out of 4 or 25% chance of getting any question right. So this probability right here is actually the proportion that he would get right if he was just a random guesser. So we could, up here, we could say Jake as a random guesser. That is the same as saying that the proportion of correct guesses or correct answers would be 25% or 0.25. And this would be that Jake is better, so he guesses with higher proportion or higher percentage or higher probability, gets more than 25% of those choices correct. So those we could write our null hypothesis and alternative hypothesis using P, which is the true proportion. So we would define that. So we define P equals the true proportion, which is like your percentage of correct answers on this 50 question test. Okay, so that means the same thing, but that's what that means. If someone is randomly guessing on this test, that means they have a 25% chance of getting any question correct. So really, we should expect them to score 25%. So what we're going to do is we're going to do 500 simulations of Jake taking this 50 question test as a random guesser to learn what happens if he just randomly guesses on the test. So if you think about it, if we know what a random guesser looks like. A random guesser is a person who gets 1 out of every 4 questions correct. So we're going to do 500 simulations. In other words, Jake is going to take this test 500 times. So he's going to do 50 questions 500 times, and we're going to record his percentage of correct answers on that 50 question test every time he does it. And that's going to help build our distribution of what we expect to happen if someone who's a random guesser takes this test. So let's take a look at this. So our hypothesized percentage is that he's gonna get 25% of his questions correct. When it says number of samples to add, that means the number of tests for Jake to take. So right now, Jake is just going to take one test. So let's see what happens when Jake takes his first 50 question test. So his first 50 question test looks like Jake's score was a 24%. Okay. So remember, Jake's a random guesser, so 24%, that's pretty close to getting 25%. So he got 24% of his 50 questions correct, which is the same as him getting 12 out of those 50 correct. So um, that was his first test. So now he takes another test. So that's his first time. Takes another one. Okay, this time he did a little bit worse. He got a 16%. So he was a little less than what we expect at 25. Okay, so that's his second test. His third test, okay, he got a little better than what we expect, which was 25%. So he got a 30% this time. So you can see, right? This is what we called, earlier in the year and stuff when we learned about sampling and this is called like sampling variability, and where every time Jake takes the test, he's gonna score likely a different score. Sometimes he'll repeat some scores, but he's not always gonna get the same score on every 50 question test he takes. So far he's taken 3 of these tests. Let's just do one more here. His fourth test, he got a 28%. So he got a little bit more than what we would expect him to score. But overall, if you look over here, the average score for him right now is 24.5%. So, like on average, he is scoring a 25% because remember, he's randomly guessing on this test. So it makes sense that his scores are relatively close to 25%. So there were 4 samples. In other words, he's taken 4 tests. I am going to add here another 496 tests. So this will be Jake sitting down for hours and hours and hours and just taking this 50 question multiple choice test and randomly guessing another 496 times. So let's see what happens when I add those in. So you can see over here, I now have 500 tests. So Jake has taken it 500 times. The average score on all of his tests is a 25%, which makes sense because we expect him to score a 25%. He's just randomly guessing. So you could see that it's like, this distribution, the approximate sampling distribution of the sample percentages or the sample proportion of correct answers. It's clustered around 25%. I mean, it should be. He randomly guessed. So what is consistent with our expectation? A random guesser, generally would score somewhere in this 25% or 20 to 30% range, which makes sense because they're just randomly bubbling circles. So the question is now, like, we know this distribution right here is what we know to be true about a random guesser on this test. So really all we have to do is think about, like, okay, what did Jake actually do when he took this real test for his friends? Did he score consistently with a random guesser, or did he score better than a random guesser would, or like sort of like inconsistent with our expectations? So let's go back and take a look at that. So when we go back here, it says when Jake actually took the test, Jake got 20 of 50 questions correct. What conclusions should his friends make about Jake's test-taking abilities under these circumstances? So Jake actually got 20 of 50 questions correct. So we call that the sample proportion. Okay, so P hat, the sample proportion of correct answers on this test is, we write that as P with a hat is equal to 20 out of 50, which is 0.40, which is 40%. Okay, so Jake actually took this and he actually scored a 40%. So think about that. We expect Jake as a random guesser, we expect his score to be a 25%. Well, he got 40. So you might be starting to sit there like, oh, well, Jake didn't pass the test, but he didn't do as bad maybe as a person who randomly guesses. So what we do is we take this and we look at, like, where does this 40% fall on our distribution? So according to our distribution here, This is if Jake just randomly guessed. Jake actually, in reality, Jake scored a 40%. Here it is, right here. Jake would have scored way out here. Look at this. Look at this. This falls in the tail of this distribution, and these tails represent occurrences or outcomes that happen with like low probability. So if Jake is actually guessing, then he really shouldn't score a 40% that often, but he did. So what we're looking at is, I said our alternative hypothesis is that they were greater than, that it was greater than or better than a random guesser. So let's look at what he actually got. He actually got a 40. So according to this, that if Jake is randomly guessing, he would only score a 40% or better about 1.2% of the time. This is your p-value. It's the probability that you score whatever your sample data is, which was 40%, or more extreme, if you are working under your expectation. And our expectation is that Jake's a random guesser. So if Jake randomly guesses, we would expect to score 40% or better only about 1.2% of the time. Since this probability, this p-value, is so low, and in fact, we have to throw in our significance level, but I just want to talk about the logic. Since this probability is so low, it's probably unlikely that Jake is randomly guessing. Like, this is probably not true for Jake. It's probably true that Jake is better than a random guesser, because this 40% is now so far away, or far enough away from our expectation, which is 25, to say that, this doesn't really occur with much probability over here. It's pretty unlikely to happen. So this 25% is probably not correct. And the way this all ties together with the significance level is we set that as called alpha. You set that at the beginning of your hypothesis test, and we just compare it. And usually it's our own thresholds, and we'll do some more learning about how to compare that. But you really just compare your p-value to alpha. So like at a 5% level, significance level, all we need is the probability here to be less than 5%, and we would reject our initial or null hypothesis that Jake is a random guesser. If this significance level, let's say, was 1%, well, if you look at what we got, it would actually be 1.2%. It's not smaller than 1, so we wouldn't reject. But the logic in general that I want you to understand is that all you're doing is comparing like the likelihood of your sample data or more extreme occurring if you are working under your initial expectation or your null hypothesis. So since this is what we expect for a random guesser, and Jake actually scored way out here, then we're starting to believe that Jake is probably not a random guesser. Like, he's scoring better than what we would expect him to score. And I think it would make more sense if I said, like, well, what if Jake took this test and he scored a 26%? Well, if Jake scored a 26%, 26% is really close to 25. Like, I don't think anybody would be able to say, that Jake is doing any better than a random guesser. I mean, he's almost perfectly a random guesser. But you can see your p-value is almost 48%. So it's like this occurs with a really high probability. Your data are more extreme. And so we wouldn't be able to reject our initial expectations. So I want you to remember, and I hope this helps, I'm crossing my fingers, that we know what to expect, and all we're doing is comparing what actually happened, which in Jake's case was a 40, which gave us a really, really low probability of occurring compared to what is expected to happen. So since Jake is far enough away from the 25% expectation, we're probably going to lean toward Jake being a little bit better than a random guesser.